Adaptive Binary Ternary Quantization by Ryan Rosani, Grégoire Morin, Ayub Sari, and Vahid Partovinia from Huawei Noah's Ark Lab, Montreal, Canada. Neural network models are resource-hungry, thus it's difficult to deploy such deep networks on devices with limited resources like smart wearables, cell phones, drones, and autonomous vehicles. Low-bit quantization such as binary and ternary quantization is a common approach to alleviate these resource requirements. Ternary quantization provides a more flexible model and outperforms binary quantization in terms of accuracy. However, it doubles the memory footprint and increases the computational cost. Contrary to these approaches, mixed quantized models allow a trade-off between accuracy and memory footprint. In such models, quantization depth is often chosen manually, or is tuned using a separate optimization routine, which requires training a quantized network multiple times. We propose smart quantization, an adaptive combination of binary and ternary quantization, in which the quantization depth is modified directly via regularization function so that the model is only trained once. We propose a generalized adaptive regularization function that switches between binary function shown in equation 1 and ternary function shown in equation 2, with a trainable scaling factor mu and order coefficient p, which denotes the type of regularization function, and a trainable shape parameter beta, and can be expressed in equation 3. The shape parameter beta controls the transition between equation 1 and equation 2. We added tangent to our parameterization for better representation and numerical stability. A large value of tangent of beta repels estimated weights away from zero, thus yielding binary quantization, and a small value of tangent of beta encourages zero weights. We also regularize parameter beta about pi over 2, preferring binary quantization a priori by adding cotangent of beta to the objective function, which is defined in equation 4. The introduced regularization function is added to the empirical loss function and makes other regularization functions like L1 and L2 unnecessary. The objective function is optimized on set of parameter weights W, set of scaling factors mu, and set of shape parameters beta using backpropagation. During training, weights are naturally pushed to binary or ternary values depending on the value of parameter beta. Eventually, a threshold delta close to pi over 2 defines the final quantization depth, which is shown in equation 6. Figure 1 illustrates the proposed adaptive regularization function. Validation accuracy for each method is reported in Table 2. Proposed SQ is on par with its full precision counterpart and beats pure 2-bit network TWN in terms of accuracy. It recommends 3 1-bit layers for VGG7 and 7 1-bit layers for VGG16. It's worth noting that the compression ratio of proposed SQ is significantly higher than the ternary network. The weight distribution of each layer of VGG7 is shown in Figure 3. Weights are pushed to a binary representation when the shape parameter beta is close to pi over 2. The proposed smart quantization is a training method which builds 1 and 2 bits mixed quantized deep neural network. Depth optimization requires training network multiple times, which is costly, especially if the network is complex. However, our proposed method successfully combines quantization with different depths while training the network only once. We focus on layer-wise quantization since it's more suitable for mixed precision inference implementation. But subnetwork, block, filter, or weight mixed quantization is feasible using a similar algorithm. SQ makes manual tuning of quantization depth unnecessary and allows to improve the memory consumption by automatically quantizing the layers with smaller precision. In some cases, it even outperforms pure ternary networks in terms of accuracy due to a formal regularization function that shapes train weights toward mixed precision. It's well known that some layers are more resilient to aggressive quantization. Our proposed methodology offers a network similar to pure ternary, but gives an insight about which layers can be simplified further by adapting to binary quantization. Thank you.